Hey everybody, Mr. Piercy here, and what we're going to be doing today in this video is taking a look at the properties of similar solids. Now, similar solids is going to follow along with things that we've done in geometry at different points in the curriculum with similarity. You may have done similarity with dilations as a transformation, where that's primarily where we use the term scale factor to show that something is either an enlargement or a reduction. We also have surface area, or we've done similarity with straight up just a unit on similar figures, whether it's a triangle or a quadrilateral or whatever the case is, where we primarily set up and solve proportions to find the value of a missing side. We talk about similar or areas of similar figures. So if I take, say, a triangle and I enlarge it or I reduce it, how does that affect how does the value of those changes affect the area? And specifically, one of the things that we're looking at here, if you read the vocabulary or if you read the definition of similar solids, what it's specifically talking about is it's the relationship of the corresponding linear measures. Okay, that is what we use to determine the scale factor of similar objects, not the areas and not the ratio or not the volumes. It's the ratio of those linear measures. So when we talk about areas of similar figures, we don't use whatever those ratios would be for the areas to say, well, that's going to be the scale factor. Same thing here when we start talking about volume. We're only looking at the corresponding figures. So like, or the corresponding sides. So 7.5 and 5, those sides correspond to each other. The 6 and the 4, those correspond to each other. The 3 and the 4.5, those correspond to each other. Those are the linear measures that we're going to be looking at when we try to determine our figures similar to each other and what those, what the scale factor, quote unquote, is of two objects. So here we're looking at a prism that's given to us. Here's the original. And we're going to be looking at that one, and we're going to compare it to both the prism here and the prism here with their corresponding sides. Well, if I look here, in order for me to be able to say two figures are similar to each other, they all have to have the same ratio. Well, if I look at the ratio of the lengths, I get a 5/10. Well, the thing is that you have to simplify that ratio if you can. So the greatest common number between the 5 and the 10 is obviously a 5, so that ratio or that fraction simplifies to be 1/2. Same thing with the ratio for the widths and the heights. Because all the corresponding sides do simplify to be the same ratio of 1 to 2, that is what allows me to make the conclusion of saying, yes, those two prisms are in fact similar to each other. Okay, if at any time the ratios don't match, at any point, everything can match except for one ratio. As long as that one is out of sync with the others, it's not going to be similar. So here, looking at the ratios of the new figure, figure B, I have a ratio of 5 to 15 that simplifies to be 1/3. Same thing with the widths, it simplifies 3 to 9 simplifies to be 1/3. However, the heights, if I compare the corresponding heights of the two figures, that ratio still simplifies to be 1/2. So because the ratios don't all simplify to be the same number, that makes me conclude that no, those figures are not similar to each other. So at this point here, go ahead and pause the video when you're ready and look at the corresponding values of these figures and determine whether or not they are similar. So go ahead and pause the video now, get your answers, and when you're ready, hit play again. All right, so hopefully we have some answers determining whether or not these figures are going to be similar to each other. So what we want to do is we want to look at the ratios of the corresponding sides, so, or the corresponding linear measures, I should say, in this case, because we don't really have sides like I would in a polygon or in a polyhedron. So I'm comparing the radii of the two figures. So I'm writing the ratio of the small one to the big one, but it doesn't have to be that way. I could have written the ratios from the big one to the small one. That's, you know, it works out the same either way. So the ratio of the radii is just 3 to 5. Now, 3 to 5 doesn't simplify, so that's just what the ratio is. If I look at the ratio of the corresponding heights, I get a ratio of 4 to 10. Now I do have to simplify that, and it simplifies to be 3 to 5. So in this case, because the corresponding radii and the corresponding height, which are the only values that really matter in a cone, especially if we're talking about determining volume, those ratios correspond to be the same value, so I can conclude that yes, these are in fact similar to each other. Now I look at the cones. With the cone, I'm giving the radii and I'm giving the heights of the cones. And when I look at those ratios, again, I'm writing my ratio as 2 to 5 to a small one to the big one. You could have written yours as the big one to the small one. It doesn't make a difference. The ratio would still work out to be the same either way. Here I get 1/2. If you did it the other way around, if you took the reciprocal of the ratios, you would get 2 to 1. But here, because the ratio of the corresponding measurements simplified to be the same ratio, again, I can conclude, yes, those cylinders are similar to each other. Well, here at this point, this is really going to be the meat, the heart of this particular lesson, where we're looking at the ratios of corresponding objects. Now, this ratio right here, this ratio A to B, this is the ratio of sides, the linear measures. This is where what we look at when we say this is our scale factor. We're looking at the ratio of the linear measures. Well, this one here, and let's do green, this is the ratio of areas. And what it's telling us is that area, that ratio, that changes by the square of the scale factor. And the last ratio that we're given here, and let's do purple. This ratio here, this is the volume ratio. And what that tells you is that volume changes by the cube. That changes by the cube of the scale factor. Now, these two things combined have a thing in physics known as the cube square law. That basically says that if I double the dimensions on something, the area gets 4 times as big, and the volume or the weight of an object will become 8 times as big. And the way that we look at this here is, so let's say this is let's say we have some object that are similar to each other, my linear measures. There we go. Otherwise known as my scale factor. Let's say that we have a ratio of 2 to 3. 2 to 3. Piercy, I can't spell, can't write today. 2 to 3. Okay, well, if I wanted to know the ratio of the areas, according to this rule here, which is something that we've seen previously in two-dimensional areas, the ratio of the area, if area ratio changes, or if area changes by the scale factor squared, I'm going to square both of those numbers, and I'm going to say 4 to 9. Well, if I look at the volume ratio depends on the scale factor. It has nothing to do with the area ratio. The volume ratio also comes from the linear measures, and this rule says that the volume changes by the scale factor cubed. So I'm going to cube that 2/3, so 2 cubed is 8, 3 cubed is 27. And that's how we would take those linear measures and find the area ratios or the volume ratios. So that's exactly what we're going to be taking a look at in this example here. they're telling us off the bat that the two cylinders are similar to each other and that the ratio of cylinder A to cylinder B is going to be 2 to 5. So they're giving us the ratio, or they're giving us the square, the surface area and the volume of the smaller cylinder, cylinder A. And we want to use the fact that we understand that the ratio of the corresponding figures changes by the scale factor squared for area and the scale factor cubed for volume. So they're giving us the scale factor. Here, this is the ratio of the linear measures, otherwise known as the scale factor. So that's what I'm going to use to find the ratios of the areas of the corresponding figures and the ratio of the volumes of the corresponding figures. And as long as I have those ratios, then I can use them to set up proportions to find missing areas or missing volumes. And that's exactly what we're asked to do here. So the stuff that we're going to do on the left is giving us already a ratio for the surface area of the two figures. So the ratio of the surface area for figure A and for figure B. Well, we have to use the ratio that was given to us and square it in order to get the numbers that we use in our proportion. Well, the ratio on the left side, they're substituting the value of the surface area that was given to you to be 96 pi. And we have to figure out, well, what is the surface area of the other larger cylinder? Well, I'm going to take that scale factor that they gave us and we're going to square it. So 2/5 squared is 4/25. Then I cross multiply, so 96 pi times 24, I'm sorry, times 25, and that gets divided by 4, is going to give me a surface area of 600 pi feet squared. And that's a typo. That should say squared, not cubed. Well, now we're going to do the same thing. We're going to take the ratio that was given to us for the linear measures, and we're going to cube it now in order to find the ratio of the volumes. So they're setting us up with the volume of A over the volume of B. So I say A cubed over B cubed. Now when I cube those numbers, now they're already substituting the 128 for the volume that was given to me for cylinder A, but when I cube the ratio that was given to me, 2 cubed is 8, 5 cubed is 125. So now I have my proportion that I can cross multiply with and show that the volume of the larger figure is 2,000 pi feet cubed. And that's how we're really going to be using the ratio of the corresponding sides or corresponding linear measures to help us set up and solve proportions for area or volume. Well, here now we're going to kind of do the same thing, except we're working backwards a little bit. They're giving us a ratio of 2, or they're giving us 2 cones that are similar to each other. And the way that they're setting up the ratio is they're saying the small one to the big one, which is fine. You can set it up that way. There's nothing saying you have to do it that way. You could take the reciprocal of it and say the big one to the small one. But first thing I'm going to do, I recognize that the ratio 108 and 256, those are both even numbers. So the first thing I'm going to do is I'm going to simplify those. Now when I simplify those fractions, I get 27 over 64. At this point here, what we're going to do, in order to go backwards, in order to go from something cubed to something that is a linear measurement, what we're going to do is we're going to take the cube root of those numbers. So I'm going to say the cubed root of 27, and I'm going to say the cubed root of 64. Now, neither of these numbers are super big. They're both something that you could probably do mentally and say, well, what number do I cube to get a 27? Or what number do I cube to get a 64? Now, that's how you would type it on your calculator. You would say the cube root of 27, or you'd say the cube root of 64. Now, some people, the calculators are a little weird sometimes. Cubing things are usually pretty intuitive. They're pretty easy to do on the calculator, but doing a cube root or a fourth root or something like that might be a little bit more challenging. But if I'm not sure where the cube root button on my calculator is, I can say 25 to the 1/3 power, or I can say 64 to the 1/3 power. That'll produce the exact same thing as taking the cube root of them. So anyway, the cube root of 27 and the cube root of 64 simplifies to be 3 over 4. So the ratio, the scale factor that we have for the similar cones is 3 to 4 or 3/4 or 4/3, depending on the ratio, how you want to write them. So now moving on to these example problems, go ahead and take what we've looked at so far and pause this video and work out these two questions. And when you're ready, hit play and compare your work and answers with mine. Okay, so hopefully we have our answers all worked out and we've done our work all nice and neat, ready to go. So here they're giving us another example. They're saying cones A and B are similar with a scale factor of 5 to 2. Find the surface area and volume of cone B, given that the area of cone A is this and the volume of cone A is this. So same idea as what we did before. We're going to take the surface area equation. I'm sorry, not equation, but we're going to take the ratios of the surface areas. We know one, but we don't know the other one. Well, if I take the 5 to 2, if I take that ratio and I square it for the areas, I get a ratio of 25 to 4. Then I cross multiply and divide. And so the surface area of cone B is 376.992 centimeters squared. Well, for volume, I'm going to take that same ratio and I'm going to cube it. So 5 over 2 is going to give me 125 over 8 for a ratio to the volume. And again, I'm going to cross multiply and divide. And here I get 476.858 centimeters cubed. Moving on, the two cylinders here are similar. Again, find the scale factor. So S is 288 inches squared. So they're giving us enough information for me to be able to identify what is the ratio of the surface areas. Well, with the ratio of the surface areas, we can figure out what the scale factor is. What is the ratio of the linear measures? Now, pay attention to how they're asking you. They're specifically saying they want it in the ratio of cylinder 1 to cylinder 2. Okay, so cylinder 1, the ratio here, that goes on top of my fraction, or that's the number that gets written first if I use colons. Here, because cylinder 2 is written second, that's the one that's going to go on the bottom part of the fraction. Whatever's written first goes on top, whatever's written second goes on bottom. It's just, that's how simple it is to write the ratios. So now, how do I look at this? Well, first of all, I'm going to take the ratios. Since they want it 1 to 2, I'm going to say 288 over 128. And that fraction simplifies to be 9/4. Well, because I'm finding the scale factor and they gave me the ratio of an area changes by the scale factor squared, so I take the square root of that ratio to find the ratio of the sides or the ratio of the linear measures. So the scale factor in this case is 3 to 2. So now we're going to be looking at similar solids, and this is personally one of my kind of questions that I like to ask. This is a good application question about, like, if you ever go to the grocery store, like, you know, here, the local grocery store, if you go to them, you can look at, like, say, cereal boxes or bottles of olive oil or something like that, and they always have some that are smaller or bigger than others. Well, usually on the price, it'll tell you how much it costs per ounce. And if you look at the bigger bottle of something, well, let's look at olive oil. Maybe the little bottle of olive oil is like $3.49. Well, the big bottle of olive oil might cost $5.25 or something like that. So you pay more for the big one. And you're like, well, I don't know if I need it. But if you look at the price per ounce, you realize that the big bottle is typically going to be a better deal because you might spend, you know, 30 cents an ounce as opposed to 57 cents an ounce or something like that. And that's what these questions here are kind of getting at. So a store, in this situation, a store is selling balls of string, and you know, maybe this is yarn or something like that that they're selling. The diameter of the larger ball is 1.5 times the diameter of the smaller ball. So there's our scale factor. They're giving us a scale factor of 1 to 2, or 1 to 1.5, or 3 to 2, however you want to think of it. So the large ball of string costs $4.99, and the small ball of string costs $1.49. So what's the better deal? Which one is going to give you the most bang for your buck? Well, if I look at the ratio of 1 to 5 to 1, that tells me that, or if I take the 1 to 5 to 1 and I cube it, because 1 to 5 to 1, that's the ratio of the linear measures. That's the ratio of the diameters. So if I cube those to get the ratio of the volumes, that gives me about 3.375 to 1. So that's the ratio for the volume. Well, I'm going to use that volume ratio now to look at the prices. How am I going to compare the prices? Well, the price of the large ball is $4.99. Price of the small ball is $1.49. So I write that as a ratio, and then I set it equal to, or approximately equal to, the ratio of the volumes of 3.35 to 1. Well, here, when I simplify that, or that's what I'm going to use rather to, if I look at, I'm sorry, let me backtrack a little bit. The $4.99 and the $1.49, that ratio, I'm simplifying that ratio on my calculator. If I simplify the ratio $4.99 to $1.49, that simplifies to be about $3.35 for every $1 spent for the small ball. So now here we're going to compare them. If I look at the ratios of the figures here, it's going to cost me $3.35 for an equivalent for about 3.375 times more string, more volume than it would for the smaller volume or the smaller ball. So in this case, the volume of the string will be a better deal, because it's going to cost me, I would have to spend 3.35 times the amount of money for the buying small balls as opposed to buying the larger ones. So here, go ahead. This is our last question for the lesson. Same idea. They're selling us cubed bird seed blocks. At this point, go ahead and pause the video and try to see what the ratios of the figures will be compared to the ratios of the cost, and see which one is going to produce a better deal. Go ahead and pause the video and work this one out. Okay, so hopefully we have our ratios worked out. So the way that I'm looking at this is, the first thing I'm going to do is I want to know what's the ratio of the costs. So the dimensions that they're giving us are 3 inches and 5 inches. So I looked at the ratios as being 5 to 3 because I'm looking at going from the small one to the big one. So if I look at the ratio of 5 to 3, I have to cube those numbers in order to get the ratio of the volume. So the ratio of the volume is 125 to 9, or about the ratio of the, or that's telling me is that the bigger block of birdseed is almost 14 times the volume of the smaller block of birdseed. So I'm getting almost 14 times more with the big one than I am with the small one. Well, the ratio of the costs of $5.99 to $1.99 is about $3 and a penny. So that effectively lets me know is that I'm going to get almost 14 times more volume for about 3 times the cost. So I can spend about $3 more $3 more per ounce, or $3 more per whatever the measurement is on the price tag, or like on the box it says, so many ounces of birdseed. But we're going to get almost 14 times more volume for only about $3 more than what we would have paid for the small block of birdseed. So we are getting a little bit better of a deal buying the larger one than the small one. Now, of course, obviously, real world, you have to look at it and say, well, how often do I actually use this stuff? And, is it really worth the cost? It's the same thing with bottles of soap and shampoo and stuff. You can always buy like the family size bottle, even if you're single and you don't, just buying stuff for yourself. Still, it's going to be long run, it's going to be less per ounce, or whatever the unit of volume is that they're giving you, than the smaller one is. So, but again, maybe you're only going to use it once a month, so it's not really worth paying all that much. But generally, the larger boxes or packages will be cheaper per ounce or whatever than the smaller ones will. So that's what that one is kind of going on. But in that case, they're just letting you know how much more are you getting versus how much it costs. But that's it for similar solids. The main point of this particular material is to, again, reinforce the idea is that similar solids The area, of course, changes by the scale factor squared, and the volume changes by the scale factor cubed. So we have to cube or square whatever our ratio is of our linear measures to find the ratio of the sides or the areas and the volumes. But that's it for this video, ladies and gentlemen. If you have any questions about anything, by all means, let me know. But until next time, take care and be good.